Alright guys, good afternoon. So we need to start today, which we had been preparing for since past 1.5 months, the processor design. But before that, I'd like to quickly go over whatever we have discussed so far, very quickly. So we know that the information is encoded in binary bits. Low voltage corresponds to 0 and high voltage corresponds to 1, and there is always 1 bit per wire. If you have like a 32-bit data, it means that there will be a 32 wires to represent that data. Similarly, multi-bit data encoded on multiple wires is generally referred as buses. We have also talked about combinational elements like AND, ALU. It operates on the data. Output is a function of input. And the sequential elements, that is also called the state elements, and like registers or memory, we use those elements to store information, and they operate on at least 2 inputs: the actual input data as well as the clock. Okay, and we have already discussed that why do we use the clock signal? To synchronize the activities, synchronize the multiple outputs that it can produce. Okay, let's do a quick review of the building blocks we have studied. It's just like a Lego blocks which we had been discussing so far. So now you know all the information about the blocks. You can integrate them together, use them appropriately to construct the big design, which is the processor design. So let's start off with these 2 basic components, which is the AND gate and the multiplexer. So AND gate, you know, it produces y equal to 1 when both a and b are 1. Okay. Similarly, multiplexer, it helps us route in the data at input A to the output C when the select signal is 0. Okay, so it just acts like a gate, the real the door which controls which input to connect to output, okay, depending on the select signal. So when S is 0, whatever the data of A, it will be routed to C, or when S is 1, whatever the value at B is, it will be connected, it will be placed at the output C. Okay. We also discussed the ALU. So ALU used to perform arithmetic and logical operations, and because we are dealing with the 32-bit data, so both the inputs of ALU are 32 bits wide, and the output, of course, would also be 32-bit. And these 4 bits are the control signal, which helps us decide what operation we need to perform, whether it's an addition, subtraction, or logical operation, or whatever. The internal structure of ALU looks something like this, and we have already discussed this in detail. You can see this A invert, B invert are the 2 out of these 4 control signals, and then we have the operation bits, which are also 2 bits wide. Okay. And we know that this B invert signal is actually tied to the carry in also. I'll show you later. So this helps us perform addition, subtraction, and or and some other logical operations. So the internal structure of this adder looks something like this, which has 32 1-bit adders each. And we have this, you can see A invert and B negate signal goes into the B invert signal as well as in the carry in. And then these 2-bit operation signal decide which operation to perform. This is actually controlling the multiplexer inside it, this multiplexer. Okay. And to perform the branch instruction, what do we do? So in the branch instruction, let's say BEQ. So what is the format of the branch instruction? BEQ X1, X2, and then the label. So what do we do actually in this branch equal instruction? We compare the results of the contents of 2 registers. If they are equal, then take the branch. Okay. And how do we compare? By subtracting the value X1 and X2. When we subtract, if the result is 0, all the 32 bits are 0, then we convert it into a 1-bit result through passing through the OR gate. It generates a 1-bit output, and then passing it to the invert, which tells that the result is 0 or not. Okay. Again, I will recall these diagrams again when we will reach to that point. Okay, so apart from this ALU, we will also be using this component, a simple adder. Okay, so whenever you see something like this add, you just assume that whatever at the input, 32-bit, usually it is a 32-bit input data, input port number 1, port number 2, whatever we provide, it will be added, and the results are produced at the sum output. Okay, we will be using this component separately also. Another important component that we are going to use is the immediate generator. Okay, so it has a 32-bit input data. It takes the 32-bit instruction. It will fetch the 12-bit immediate value. Okay, we are not going into the details how is it going to do that, but it will fetch the immediate 12-bit value, sign extend it to 32-bit, and produce it here, place it at here. Okay. So this is how the immediate generator would work. Again, the immediate generator, why do we need it? Because there are instructions in which we have the immediate data, and it is always in the 12-bit format. Okay, so we extract the 12-bit immediate value. We need to extend it. We have already been discussing that 12-bit data is always a sign extended, 32-bit sign extended. Okay, so this unit will extract the 12-bit value, sign extend it into 32-bit, and produce it at the output, and then we can use this value. This is now a 32-bit immediate value. Okay. Sequential components is the register which has 2 ports, D input, whatever data we provide, and if you want to write it, we set the write signal to 1, and it will write the data placed at this D input port. Okay. If you want to just read it, we can just read it with the help of the Q port by providing what register we want to read. Another important thing we discussed when we were discussing the assembly language, remember PC, the program counter. What does program counter do? Can we quickly recall? What is the purpose of program counter? Program counter. You had that in your exam as well, in the midterm exam. Want to say something? Program counter? Like a loop counter? No. You can, in other words, you can call it loop counter, but what does it point to?
The stack.
No, not a stack. Yeah.
Next instruction.
Yes, the instruction that is to be executed next. It contains the address of the instruction that is to be executed next. So it's simply a register. It's a 32-bit register. It will only contain the address of the next instruction. Okay. Then in the last week, we also discussed that we will be representing register file with this block diagram. Okay. So we have the register, read register number 1, read register number 2. We specify what value, what register we want to read, and the corresponding data will appear on these ports. Okay. Similarly, where do we want to write? We specify that register number here, and what do we want to write? We will provide that data here. So what should be the width of these ports? What about these 3, the first 3? Read register number 1, read register number 2, and write register. What are the width of these ports? We have already discussed this. So think of an instruction format, instruction encoding. We have already discussed in the 32-bit instruction, what is the width of RS1, RS2, and RD? 5 bits. So in the 5 bits, you can specify what register you want to read. Okay. And why 5 bits? So that we can access 2 to the power 5 register, any of the 2 to the power 5 register, which is 32. Okay. So with the help of this 5 bits, we can specify what register we want to read, and the contents will be placed here. And where do we want to write? So we have to specify the RD field here. Okay. So it's just like you can assume that the instruction, 32-bit instruction, the RS bit field will be going into this port. RS2 field, the 5 bits, the 5 wires coming from that RS2 field will be going into this port. Similarly, for the write register, it will be going to this port. Okay. What about this write data? What should be the width of this write data and read data 1 and read data 2? Yes, 32 bits, because we want to write a register. It should be a 32-bit value because the size of the register is 32 bits. Similarly, what do we want to read? It will also be appear in the form of 32-bit data. Okay. So program counter, register file, and another component required is the data memory. Okay. And when do we use this data memory? What instructions requires us to access the data memory? Come on. Store and load instructions. Okay. So in whatever the instruction we are using, these control signals will decide whether we want to read the data from the memory or write the data into memory. So mem write signal signifies that we want to write the data in the memory, and that instruction is a store instruction. Okay. So what we do is we provide the address and we provide the data where do we want to write, and we can just write the data into memory. Similarly, when you want to read the data from the memory, again, where do you want to read the data from? You have to provide the address, and you need to set this signal memread because you want to read, and the corresponding data will appear here. Okay. And the width of this these ports will also be 32-bit. Okay. And another thing is the instruction memory. So we have also discussed that the instructions are also stored in a memory. Previously we discussed that it could be some portion of the main memory, but soon you will see that we will be treating instruction memory separately with the data memory, and why we will discuss that later. But assume that this instruction memory block will only be containing instructions. Okay. So when it is containing only instruction, so mem write signal will always be 0 because we are not writing anything in this instruction memory. During the execution of a program, we will only be reading instructions one by one. Okay. And how do we read the instructions one by one? With the help of that program counter. It will keep incrementing. After reading one instruction, it will increment by 4 and then again by 4. Okay. Any question here? Again, in this lecture, you need to concentrate because many of the things I will be talking, I cannot write everything on the slides. So I will be explaining things by looking at the diagrams. Okay, so this is also 32 bits. Okay, the instruction address is 32 bits and the instruction is also itself 32 bits wide.